again. We are in the last lecture of week 5. We are in the middle of doing logic coverage criteria based testing. I defined what the various logic coverage criteria are and showed you their subsumption relations. Today what we are going to see is, suppose you have to take a real program and use this logic coverage criteria to actually correctly write your test requirements and subsequently define test values. How would you go about doing it? So just to recap what we saw till now, here is all the logic coverage criteria that we saw. We began with predicate and clause coverage, the most elementary form of logic coverage. Predicate coverage says test for the predicate to be true once and false once. Clause coverage says test each clause to be true and false once. Then we saw all combinations coverage right on top in terms of subsumption. It says test for the entire truth table of all the clauses in the predicate. We said that's too expensive because it leads to an exponential number of test cases. So what can we do in between? The in-between coverage criteria are broadly classified as active coverage criteria on the left hand side, 3 kinds, and inactive coverage criteria on the right hand side, 2 kinds. Both these cases, the premise was choose one clause at a time in the predicate, call it the major clause. And in active coverage criteria, major clause determines the predicate. The minor clauses take values such that the major clause determines the predicate. In inactive coverage criteria, the minor clauses take values such that the major clause does not determine the predicate. So this is a summary slide that contains all the logic coverage criteria that we saw and how they are all related to each other, what subsumes what and what does not subsume what. The focus of today's lecture would be to design test cases. So we'll take one at a time and then see how to design test cases. We saw during the logic coverage criteria lecture that we did as a third lecture of week 5, these how to design test cases for clause and predicate coverage and for all combinations coverage. They are reasonably easy because as long as a predicate is not always true, which means a predicate is not valid, or as long as a predicate is not always false, which means the predicate is never valid, which means it's a contradiction, it's always possible to get test cases that will do coverage criteria for both predicate coverage and clause coverage. You have to identify a set of values that will make the predicate or the clause true once and another set of values that will make the predicate or the clause false once. For all combinations coverage, it's again easy. Write out the entire truth table and then write test cases for every row in the truth table that will make each of the clauses true and false in turn. Right? The only problem that we might have to solve is, suppose there is a predicate that comes deep down in a program as a part of an if statement, which is way down in the program in the sense that it comes, let's say, after a few hundred lines in the program, and it so happens that the variables that you encounter in the if statement, none of those variables deal with input values directly. So I should be able to give inputs to the program, first of all, to be able to reach that if statement and exercise my desired coverage criteria for the predicate in that if statement. So you remember, right, in the first week we saw this thing of observability and controllability, and then I told you about RIPR criteria. So we will have to do reachability and then we'll have to do infection to be able to achieve our coverage requirement and in turn propagation. So what we'll do in the next week, the first module that we will see, we'll look at logic coverage for source code. Take a piece of program, look at all the predicates in the program and see how to apply the coverage criteria that we learned. At that point, we will deal with this last item here of reachability or RIPR criteria in detail, which basically means that if a predicate in a program deals with internal variables that are not inputs, how to give input values that will make the program reach and achieve the desired coverage criteria on that predicate. So now, what about designing test cases for the rest of these coverage criteria? For the 3 active clause coverage criteria and the 2 inactive clause coverage criteria. The first thing to do and remember is that for active clause coverage criteria, we choose each clause to take turn as a major clause, and the minor clauses take values such that the major clause determines the predicate, right? So now what we will do is how to make a major clause that is chosen at any point in time determine the predicate. Now, major clause determining a predicate means the predicate should take true or false values as and when the major clause takes true or false values, right? So we'll see how to do that by using examples, and then based on that how to choose TRs and test cases that satisfy the TRs. So what I'll do is I'll walk you through several examples that tell you how to make a major clause determine a predicate. In all these examples, we'll do a generic definition based approach of deciding when a major clause determines a predicate. So here is what we do to make a major clause determine a predicate. So you consider predicate P, and let's say there is a clause C in the predicate P. I want C to be the major clause, which means to be able to do active clause coverage criteria, I want C to be able to determine P, and when I do inactive clause coverage criteria, I want C to be able to not determine P. For the purposes of this lecture, I will focus on active clause coverage criteria and tell you how to make a particular chosen clause, which is the major clause, determine a predicate P. So I fix a predicate P and I pick up a clause C in that predicate, call it the major clause. The idea is when will C determine P? For small predicates it will be easy, but for large predicates it may not be easy to know when exactly C will determine P. So we use a default definition based approach, which is like a set of steps that you need to do to make C determine P. So here are the steps. So what we'll do first is we'll take the predicate P, take every occurrence of C in P. By the way, without loss of generality, I'll assume that in all the predicates that we see, a particular clause occurs exactly once. If it occurs more than once, the second occurrence is usually redundant and we remove the second occurrence. So what I do is I take the predicate P, consider the place where the clause C occurs in the predicate P, and replace C with true. So call that resulting formula or resulting predicate by this notation. P subscript C is equal to true. So now the second thing that I do is I take the predicate P, consider the clause C, replace C with value false wherever C occurs, and simplify the logical formula corresponding to the predicate. Call that as PC false. So is it clear what PC true and PC false are? PC true means take the predicate P, consider an occurrence of C in P, replace that occurrence with true and simplify the formula. PC false says take the predicate P, consider the occurrence of C in the predicate P, replace C with false. Right? So once I replace C with true or false to get these two predicates PC true and PC false, please remember that P has no more occurrences of C. C is completely eliminated from the predicate P. Now I define the following formula PC. I take this formula PC true and XOR it with the formula PC false. Read this notation that looks like a lens of this thing as XOR. You remember what XOR as a logical operator is? XOR says A XOR B says that it will be true exactly when one of A or B is true, right? So XOR OR says that it will be true when one of them is true. It could be the case that both of them will also be true to make an OR true. XOR is exclusively OR. Exclusive OR means a particular A XORed with B is true if and only if exactly one of A or B is true, right? So I take P, fix a clause C, my major clause, take copy of P, replace C with true, simplify the predicate, keep it on one side. That is PC true. Then I take the same predicate P, replace the clause C with false, simplify it, keep it on one side. That is PC false. Now I XOR these two formulas, call it PC. What do we do with PC? It turns out that PC describes the exact conditions under which the value of C determines P. Why is that so? That's so because if you see the clauses that occur in PC, first of all C is not there. They take values such that when PC is true, C will determine P in terms of its truth values, and the clauses in PC take values such that when PC is false, P's truth or falsity is independent of the truth or falsity of C. Why does this happen? Instead of doing a proof, I'll show you several examples of how to take a predicate and a clause, how to determine PC, and understand why PC will represent the conditions under which the clause C determines P. So here is a first formula. So the predicate that I want to illustrate by using an example is this predicate. I have taken the predicate P, which is A or B. How many clauses are there in the P? In the predicate P, there are two clauses. One clause is A, one clause is B. Now I want to be able to compute PA, which means I fix A to be my major clause and I want A to determine P. So as per my formula, what should I do? I take this P and first replace every occurrence of A in the predicate P by true, and then I replace every occurrence of A in the predicate P by false and XOR them. That's what I have written in the first line here. This is as per our definition. PA is the same as P with A replaced with true XORed with P with A replaced with false. Right? What is P with A replaced with true? P in this example is A or B. So you take this predicate A or B. Instead of A, write true. That's what I have written in the second line here. So this is A or B, which is the predicate P with A replaced with true, and P with A replaced false is false or B with A replaced with false. And then my goal is to XOR them. Now, what is the semantics of true or B? True or B should basically be the same as true, right? Because true is always true, so B doesn't really influence. So true or B simplifies to be true logically, and false or B simplifies to be B logically, right? So you can look up the basic rules of inference of propositional logic, and these would be some elementary rules. So this is what is called generalization, this is what is called absorption. So true or B simplifies to true, false or B simplifies to false. And now again one more rule, I have to XOR true with B, which is the same as not B, right? Because it says what either exclusively true will be true or B will be true, right? So it should be the case that B, not B is true, or in other words B should be false. So what I have done here, I have taken the predicate P, I want A to be the major clause in P, and I want to compute PA. PA says PA is true whenever A determines P. So I used the formula that we had and substituted, simplified, and got PA to be not B, right? Now if you see, how do I read this as? I read this as follows. For the major clause A to determine the predicate P, the only minor clause B is the only other clause here, right, must be false. Why is that so? Even without working this out, if you independently see this formula here, I want A to determine P, which means what? I want P to be true or false exactly when A is true or false, right? Suppose B was true, then the whole predicate will become true independent of the value of A. So B has to be false for A to influence when P becomes true and when P becomes false. That's exactly the conclusion that we have derived by using this formula and substituting. We have derived that PA is the same as not B, or in other words, for major clause A to determine the predicate P, not B should be true or B should be false. Symmetrically, suppose B was a major clause. For B to determine P, if I replace the same derivation in the same derivation A with B, I will get not A, which means what? For B to determine P, A should be false. So we look at a couple of more examples. The second example that we consider will be the predicate P, which is now A and B instead of A or B, which we saw in the last slide. I repeat the exercise. Now I want A as my major clause and I want to know when A will determine P. So I use the formula that we learned. I say PA is the same as P with A substituted with true XORed with P with A substituted with false. So I take P, which is A and B here. I substitute A to be true. So I get true and B. XOR it with A substituted with false, which gives me false and B. True and B, if I use the rules of logic, maps to B, and false and B, if I again use the rules of logic, maps to false. Why is this so? Because true and B, true is more general and is a restrictive operator, so it will be true exactly when B is true, and false and B will be false all the time because it's ANDed with false, right? So B XORed with false as per rules of propositional logic is equivalent to B. So what have we concluded? If A is the major clause, for A to determine for A to determine the predicate P, PA is the same as B. So which means for major clause A to determine P, the minor clause B must be true. So if you put it back and intuitively look at it, suppose B was true, right? Suppose B was true, then A will completely determine P, no? Because if A is true, P will be true. And if A is false, P will be false. That's exactly what we have concluded here. And symmetrically, if I consider B to be the major clause and repeat this exercise for B, I'll get PB, which is the conditions under which B determines P to be equivalent to A. So one more example before we move on. Here I'm considering the predicate P to be A is equivalent to B, which means A if and only if B. I again want A to be the major clause and compute PA, which says when A determines P. So I use the same formula. Take the predicate P, replace occurrence of A with true, XOR it with replace occurrence of A with false. True equivalent to B turns out to be B. False equivalent to B turns out to be not B. B XORed with not B means what? Always B or not B is true, which is like a valid formula or a tautology. So this simplifies to be true. So here what has happened when we try to make A the major clause and make A determine the predicate P, the answer that we get is true. How do you read an answer like true? You read it as no matter what happens, for any value of B, if I choose A to be the major clause, A can never determine P, right? So you can come to several conclusions as we saw in these examples. For a predicate like this, I want A to determine P, then B must be false. For a predicate which looks like P is equal to A and B, if I want A to determine P, then B must be true. For a predicate which looks like A is equivalent to B, I try to make A determine P, but I end up concluding that A can never determine P. So how do I understand this thing of never being able to determine a predicate in terms of testing? In terms of testing for a predicate P, where the value of PC for a clause turns out to be true, that's what happened here, right? In this example, for the predicate P is equal to A equivalent to B, the value of PA turns out to be true, right? In that case, it means that a clause cannot determine a predicate, right? Cannot determine a predicate because the minor clauses can never take any other values. So which means what? Inactive clause coverage criteria is typically infeasible, right? Because inactive clause coverage criteria, if you remember from the previous lecture, what does it say? It says that minor clauses take values such that the major clause does not determine P. But in this case, when I end up computing PA for A to be a major clause and I get the answer true, I conclude that no matter what happens, the clause that I have chosen as the major clause cannot determine. So I cannot basically do inactive clause coverage criteria. Typically, it is known that when I have predicates with XOR or equivalence, ICC criteria turn out to be infeasible because I'll end up with these funny results like true and all that. Symmetrically, if you think about it a little bit, if I try to compute similar thing PA and then suppose I end up with false, then I can conclude that active clause coverage criteria will not be feasible. That's what I've written here in the third point. I say if a predicate P has a clause C such that PC evaluates to false, then active coverage criteria will be infeasible for P with respect to C, right? It basically means that the clause is redundant. You might as well remove it from the predicate P. So I'll show you an example here. So when do I say that a clause is redundant? Purposely, in this example, I have considered a predicate that looks like this. So what does the predicate read as? It reads as A and B or with A and not B, right? So now, what is this basically? If you use the rules of logic, propositional logic a little bit and try to simplify it B or not B are neutral, they'll neutralize each other, they'll result to be true. And you just have two copies of A, which are redundant copies of A. So P, the base predicate P, is basically just A, right? But for some reason it occurs in this complicated form like this. So if the predicate P is just A, but B is occurring in a sort of a useless form here, I want to be able to conclude that B cannot determine P. So how do I do that? I compute PB and I have to end up with false. That's what this derivation illustrates. What does this derivation illustrate? It says PB is, you do the same formula, replace B with true, XOR it with B replaced with false. So I take the predicate P, which is this. I replace every occurrence of B with true, which is what I've done here. And here I replace every occurrence of B with false, which is what I've done here. I simplify this formula. So if you simplify this formula, A and true or A and not true, you will get A or false. And here if you simplify this formula, you will get false or A. A or false is the same as A, false or A is the same as A XORed with A is basically false. So it is impossible for B to determine B, right? So it's as good as saying this B here, which occurs in the predicate P, is fairly useless, is redundant, you might as well remove it, right? So we'll go back and do one more example to understand how a clause determines a predicate, because it will be useful for you. I'll also give you, in the assignment for this week, I'll give you a set of exercise where you should work out for at least one more formula how a particular clause determines a predicate. So here is another example. The predicate that I have taken this time is P, which reads as A and B or C. Now I want to determine PA, which is basically I have chosen A to be the major clause, and I want to determine conditions under which A determines P. So I use the formula PA is PA true XORed with PA false. So I replace A with true in this predicate P, I get this. I replace A with false in the predicate P, I get this part. I now use the rules of logic to simplify. So true ANDed with B or C is the same as B or C. False ANDed with B or C is the same as false. B or C XORed with false is the same as B or C. So now what it says is that for A to determine P, B or C must be true. That's not too surprising, right? Because if you see P is A ANDed with B or C, right? So unless this whole thing is true, A cannot influence P, right? So B or C must be true. B or C must be true. You apply the condition for B or C as another formula and find out when it will be true. Use the semantics for OR. If you use the semantics for OR, B or C will be true in three possible cases. Both B and C are true, which is listed here. B is true, C is false, or B is false, C is true. So there are three choices to make B or C true. Now suppose I have to do correlated active clause coverage for A. Then what can I do? I'll pick one pair when A is true and another pair when A is false. So I can pick A to be true, and let's say I pick this B true, C true, in which case the predicate P will evaluate to true. And now A is false, I pick some other pair. Let's say I pick the pair B false, C true, right? So in which case what will happen, this whole thing will be true, and A is false, so P will turn out to be false. So A will correctly determine P. Now for restricted active clause coverage criteria, what do I have to do? I take value of A to be true and false again. A is the major clause, and I choose the same pair because that's what our ACC says, right? The minor clauses all take the same value. So I could take, for example, A to be true and both B and C to be true, in which case the whole predicate, if I substitute it back, will evaluate to true. Or I could take A to be false and B and C to be true, in which case the whole predicate when substituted back will evaluate to false. So is it clear, please, how to do PA, PB and PC? So to be able to completely satisfy GACC, RACC, CACC and other criteria for this predicate, what I have worked out in this slide is only for A. So you have to repeat a similar exercise for B being the major clause, similar exercise for C being the major clause, and then write out conditions for GACC, CACC and RACC, right? So here for the same predicate in this slide, I have worked out what happens when B is the major clause. So when B is the major clause, I'm interested in computing PB. So I take PB true, XOR with PB false. Take this predicate P, replace B with true, I get this part. Take the same predicate P, replace B with false, I get the part here. Simplify these logical formulae. You might have to remember a few rules of propositional logic to be able to do this simplification. So A ANDed with true or C is same as true, false or C is same as false. So A ANDed with true is A ANDed with C, I can't simplify it further, I keep it like this. This formula A XOR with A and C simplifies to A or not C. The last two parts from this line 25, equation 25 to equation 26 may not be very obvious. One simple way to convince yourself that 25 and 26 are the same would be to write the truth table for 25 and write the truth table for 26 and check that the truth tables are the same. Right? That's an easy way to understand why this simplifies to this. Even otherwise, if you don't know this simplification, it's okay to leave it like this. A XOR with A and C and say that this is the condition under which B determines B. Right? Because that also can be equally handled in terms of writing test cases. So similarly, because B and C come with this disjunction inside the bracket, I can do a similar exercise for PC and it will be symmetric and PC will turn out to be A ORed with not B. Right, now how to write test requirements for active clause coverage criteria. So sometimes active clause coverage criteria can get little complicated for certain predicates in terms of finding TRs and subsequently finding satisfying test cases. So I'll walk you through one final example and see how to actually do the end-to-end TR generation and test case writing for active clause coverage. So this time I have taken a similar predicate but slightly different. If you go back, the predicate we had here was A and B or C. Now what I have taken is A or B and C. You could do a similar exercise for that predicate also, it doesn't matter, but just to illustrate, I have taken another predicate. What is my goal now? My goal is to be able to, for each of these clauses, three clauses taking turns to be the major clause, to be able to find test requirements for GACC, CACC and RACC. So there are three clauses in this predicate, A, B and C. So what I do is I first write out the truth table of the predicate. It helps to write out the truth table because you can understand it a little easily. So I've written out the truth table here. The truth table has 8 rows. You can work it out for yourself as a small exercise. And I have done using this kind of working out that we did for this formula. I have calculated PA, PB and PC. I have not shown you the working. Please try it out as a small exercise. But if you use the formula PA is PA replaced with true, XORed with A replaced with false, and then use the rules of logic to simplify it, you should get something like this. Similarly for PB, similarly for PC. Now what I'm going to do, I want to be able to first do test requirements, let's say for generalized active clause coverage criteria. So let's recollect the definition of GACC. GACC definition says each major clause will be true and false and minor clauses will be such that the major clause determines the predicate. So now what will be the TR for GACC? I'm writing what I wrote in English here in terms of true false values. So the first pair here is when A is the major clause, A is true once, ANDed with A determining P, which is PA, A is false, ANDed with A determining P, which is again PA. Now the second pair here is B's turns to be the major clause, B is the major clause, so B is made true once, ANDed with P, B, which says when B determines P, B is made false one, again ANDed with PB. The third pair here is C's turn to be the major clause. C is true once, false once. For C to determine P, I specify it using PC. So here is a table that gives you the true-false values for the test requirements for GACC. So A is the major clause, first two rows. I'm sorry, there's a typo here. It should be B is the major clause for the third and fourth row. C is the major clause for the fifth and sixth row, right? So A is true ones. If you see, concentrate on the ones in bold in the table. A is true ones, false ones. B is true ones, false ones. C is true ones, false ones. The rest of the values, rest of the clauses B and C in this case, and A and C in this case, and A and B in this case, take values such that the predicate becomes true ones, false ones, true ones, false ones, true ones, false ones. So this is how I do GACC for the predicate P. Now if you look at this table, you'll see that there are repetitions. Like for example, the first row is the same as the fifth row. True, A is true, B is false, C is true. A is true, B is false, C is true. Because the assignments are the same, the predicate evaluates to be true. Similarly, in the table, the second and the fourth rows are the same. So I don't have to repeat them. So I keep only one copy for each of these. So how many tests totally are needed? 4 test cases are needed. One for row 1, one for row 2, one for row 3, and one for row 6, which is not a repeat of any of the earlier rows. So totally my test requirement for GACC for this example predicate P for each clause A, B and C taking turns to be the major clause can be achieved by a set of 4 TRs, which are basically these rows in the table. Similarly, you can work out TRs for CACC and for RACC just as a small exercise because it may not be very obvious to do. I urge you all to please work out the test requirements for CACC and for RACC and feel free to get back in touch with me in the forum if you have any doubts about working out. And you will realize after working out that for this particular example, correlated active clause coverage criteria is the same as general active clause coverage criteria. And typically for several predicates, CACC is considered to be very good to use. It's practically useful and quite a useful thing when compared to other predicates. So this will be the last lecture of week 5. What I'll do next week in the first 2 modules is we'll continue with logic coverage criteria, but we will see how it is practically useful. The next lecture we'll take a piece of program and see how to apply logical coverage criteria that we learned to test that program. And in the lecture after that, we will take a specification as a finite state machine and see how to apply logical coverage criteria that we learned to be able to test that specification, write test cases for that specification. Thank you.